issues right now, if you're a computational neuroscientist, is that it's clear that getting gradients with backpropagation and doing stochastic gradient descent really works well in big neural nets, like GPT-3 or Google's equivalents of it. And so that's a pretty good argument that maybe the brain's doing something like that. It's just nobody can figure out how the brain could be getting the gradients. And that 2020 paper, we sort of made our best attempt to figure out how the brain might be getting gradients, but it's not very convincing. I think I can say that because I am an author. In that direction, and it's a big step if it helps a lot, and a negative step if it hurts and so on. That algorithm works okay. It's about 100 times slower than backprop, and even slower when you get nets with tight bottlenecks and things. So the sort of most biologically plausible alternative to backprop, which is things like the reinforced algorithm, they don't work that well. And they're not good at packing lots of information into a few connections, as compared with backprop. And so that's an argument to suggest the brain must have something better than reinforced. I know I'm just waffling here because I don't actually know the answer, but I often talk about this with Ilya Sutskever. He's firmly of the opinion that the brain must have a really good learning algorithm because we've evolved for so long, and it's really important to have a really good learning algorithm. You get huge selective advantage from having it. And evolution can take stem cells and can turn them into teeth or eyeballs. So if it can make teeth and eyeballs out of the same cells, why can't it figure out a derivative? And so my guess is we do have a way of getting derivatives, but God knows what it is. And in the 1980s, I thought it was Boltzmann machines. So Boltzmann machines were a much more elegant theory than backprop. And I'm going to talk about Boltzmann machines in my lecture today. And I still have a niggling feeling that Boltzmann machines may have something to do with how we get gradients. But yeah, I really don't know. But it's one of the big open issues. I mean, I'd rather have the solution to does the brain use backprop than have the solution to does P equal NP. Awesome, thank you.
Oh, don't be shy, folks. Who wants to go next?
I have a question. Oh, did I cut somebody off?
No, it was me. I was about to fill in the gap, but
I feel shy, but I'm curious about what your thoughts are. I think like one limitation of deep neural networks that I've seen in my research is that they kind of tend to have unexpected behaviors, and they rely on spurious correlations, or they hack the reward they objectively give it. So I was wondering if do you think that like making more human-aligned models would be a positive direction into having neural nets that do not rely on things we do not want them to, or should we keep like human behavior and model behavior kind of separate because they each do different things?
It's a very good question, and I'm strongly of the belief that, particularly for perception, we ought to try and make neural nets that have the advantages of neural nets, that they learn everything, and that if you make a bigger one, it works better, so they scale nicely. With very little intellectual effort, you can scale them up to work better, but work more like people do, so that they're going to make mistakes more like people do, so that they behave the way we sort of understand. And I've got a long paper about that, about how to implement part-whole hierarchies in neural nets, which I put on archive about a year ago, almost exactly a year ago. And the main theme is we need neural nets to see the world more like we do, and then we won't get these adversarial examples, or at least not so badly. And they'll be more sensitive to things like the part-whole structure of objects and less sensitive to things like textures. So at present, even though neural nets are very good at recognizing things, they use much too much texture information and much too little shape information. And I have a whole bunch of nice demos to show that people really are using coordinate frames.
Yeah, thank you. That's really encouraging because a lot of my research right now is focused on how to make models more interpretable and then manipulate that to make them more human aligned. I work mostly on the linguistics and the computer science intersection, but that's very promising to hear. Thank you.
Yeah, but even on the linguistic ends, I think it's clear that if you have an ambiguous sentence, you would like your neural net to perceive it one way or the other.
Yeah.
So if I give you a sentence, next weekend we shall be visiting relatives, that's ambiguous between next weekend what we will be doing is visiting relatives, or next weekend what we will be is visiting relatives. And they're completely different senses that have exactly the same truth conditions. But we clearly understand it one way or we understand it the other way. We don't understand it both ways at once. And things like GPT-3, there's no sense that GPT-3, I think, has two different ways of understanding that and pick one. And so the same thing applies there. Yeah.
Thank you.
Hello. Okay, so my question is, in some of your talks, particularly your Turing Award lecture, you contrast symbolic or logic-based AI with the biologically inspired learning methods. And do you think that as the field and the problems that we care about in the field of AI demand more complex reasoning, generalization, interpretability, and controllability, should we move towards combinations of symbolic and learning-based methods, for example, through inductive biases? Or do you think that, do you think the future of AI is in this combination, or is this just a temporary shortcut and the field will eventually converge towards purely learning-based methods?
I think there's two very different ways of thinking about things like reasoning. You can think about hybrid systems where the kind of low-level grunt work, like motor control and perception, is done by neural nets. And then you try and preserve symbolic AI for doing reasoning, which is clearly the pinnacle of human achievement. Or you can think that it's all neural nets. There's a higher level of description of what's going on in neural nets. And that's what these symbolic models are trying to get at. But it's really all neural nets. So you know how Intel computers have a little symbol that says Intel inside? I think we should have a symbol on our foreheads that says vectors inside. There's no symbols in our heads in the sense of a pure symbol. And what I mean by a pure symbol is something that its only properties are that it's identical to other instances of that symbol, and it's different from other symbols, and that's all there is to it. That's what I think of as a pure symbol. And I don't think we use pure symbols. The only place we use those are in the input and output. Inside it's all vectors. It's these great big vectors of features. So our primary mode of reasoning is analogical, it's not symbolic. So for example, people, at least in my culture, they kind of know instantly that cats are female and dogs are male. Now this is not exactly biologically realistic. There have to be male cats and female dogs. But basically, if you have to do it one way around or the other way around, you know that cats are female and dogs are male. And that's because of analogies. Dogs are bigger and noisier and they chase cats. And so that's what I think our normal mode of reasoning is. And for example, that's why Trump was more successful than Hillary. Hillary appealed to reason, and Trump appeals to this gut analogy, and that's our basic mode of reasoning. So I think symbolic reasoning is a veneer. It's built out of this stuff. It's very important for things like doing math or making sure your bank account has the right amount of money in it. But it's not the basic thing. It's a veneer built on top. And I really don't like hybrid models which say we're going to have, we're going to relegate neural networks to doing the housework, and then we're going to have symbolic AI taking charge once neural nets have solved all the problems it couldn't solve, like how do you get from the real world to symbols. I think that's crazy. I think the symbolic level is a higher level description. It's like thermodynamics versus atoms, right? I mean, imagine if a physicist said, okay, So I finally buy the atomic theory. There are these atoms, and they sort of buzz around, and the properties of atoms to explain various things. But there's also another kind of physics, which is thermodynamics, and that's the real physics. And we'll get these atoms to sort of be the front end, but it's really thermodynamics. That's just the completely wrong view of the relationship of thermodynamics and what's going on with atoms in statistical physics. One's an emergent property of the other. And so if I have a big parallel network, however big I make it, I can always find a task that it can't solve in sort of one parallel settling down of the big network. It has to take the task and break it up into pieces, and then map these pieces onto the neural net. And the same bunch of neurons has to be able to solve different pieces of the problem at different times. And so you have to have this kind of sequential mapping of the problem onto the neural net. That's most obvious in vision, where fixation maps the real world onto your retina. It also does magnification of what's ever in the middle of whatever you're looking at. So it does zooming and translation all in one. And we do a sequence of those. And because you can see people's eyes move, you can see that they're doing this sequential reasoning, or rather, this sequential application of the neural net. And so, obviously, you just don't do everything all in parallel. You have sequential applications of these highly parallel operations. And the organization of those sequences is what we're kind of aware of, and it's what we call reasoning. But it's all a neural net. It's the organization of a neural net done by other bits of the neural net. But what's intrinsically sequential is if I've got a bunch of neurons that's used for something, I can apply it to one bit of the task, or I can apply it to another bit of the task. But I can't use the same bunch of neurons for both bits of the task at once. I have to decide which bit to do first and which bit to do next. That's sequential. And that's where all sequential structure comes from. But you can think of it as like a huge instruction set machine, where it's doing this sequential reasoning. But each instruction in this sequential reasoning is a parallel settling of a huge network and doing an immense amount of computation, including sort of immediate analogies. So, like figuring out which rule to apply next when you're doing symbolic reasoning, that's done by a huge parallel settling that's using all sorts of analogies with this situation and other situations. It's sort of one step in the sequential reasoning, but it's a huge amount of computation happening. So that's my sort of model of the relation between the symbolic and the analogical, and between symbols and neurons. We're basically analogy machines.
Alex, please.
Okay, yeah. My question is, as the compute requirements of deep learning get higher and higher, what's the role of academics or students, PhD students in deep learning?
I'm really tempted to make a joke, but I better not. Like, why do you assume there's a role? So I think still there's some things you can only explore if you can afford if you've got $1 million to spend on letting it learn. Like GPT-3 scale things a couple of years ago. In a few years' time, those things will be perfectly available to academics, I expect. But most things still are idea limited, I believe. So there's really two lines in your research. One line is just scale it up. Take the ideas we've got now, sort of modify them a bit, do lots of clever hardware and software design so you can scale it up, and do a really big one. And that's the kind of research academics shouldn't be involved in, because it's expensive. Also, you need big teams if you want to make it work. So like OpenAI, I think GPT-3 had rather a lot of authors. Academics, but I think universities are still the best place for really original ideas. Because what you want is somebody young who's been exposed to an environment where they know what the issues are and they get good feedback when they say silly things, but they haven't been so indoctrinated that they're thinking just like everybody else. They still have their own ideas and they've got the space to develop them, and they're encouraged to develop them. And so I think a graduate student at a good university is still the best source of relatively new ideas. And I think the role of professors is to facilitate the graduate students. That's my
I think I'm next. Hi, Dr.
You are, Lisa.
Perfect. Hi, Dr. Hinton. First of all, I just wanted to say it's so great to be in this roundtable with you. I've watched so many of your talks, and your talks were partly the reason I got into AI and cognitive science, so thank you for that. My question kind of touches on some questions already asked. So obviously neural networks were inspired by the human brain and neurons, and a lot of cognitive scientists and computer scientists say that we need to study neuroscience, psychology, and cognitive science more to find more developments and advancements in deep learning. But there's a saying that goes, even though airplanes were inspired by birds flying, it's not like airplane wings flap. So I was wondering what your take is on balancing studying neuroscience and psychology as an inspiration for advancements in deep learning and using more like mathematical, logical methods for advancements in deep learning.
Okay, I've got a new take. I don't know if it'll stick on aeroplanes and birds. Okay, so the Wright brothers knew to take off into the wind because they watched birds. So they did actually learn a lot from birds. And some people say, but airplanes aren't like birds because they don't flap their wings. There's another way in which airplanes aren't like birds, which is they're not covered in feathers, right? I mean, their wings aren't made of feathers, right? So it would be silly to look at a bird and say, well, we should make the wing out of feathers. Okay, now think about a drone. You have a little drone, and it crashes into things. And here's what you'd like in your drone. You'd like that when it crashes into things, it doesn't break them. But you'd also like that it's very easy to repair. Now ask how a feather works. So a feather is lots of sort of fronds that zip together. And so they zip together to make a surface that you can flap your wings with, or actually glide with, just like an airplane. And so imagine making the rotor of a drone out of feathers. You'd now get a big advantage because if the feather hits something, what happens is the feather breaks. I mean, the fronds come apart, so it can absorb the shock and it doesn't break and tear apart. And if you could get the drones to preen themselves so they zip the fronds back together again, you'd be much better off having drones whose rotors were made of feathers. So this is the biological inspiration for a safer and better kind of drone. This is just me being perverse and saying that, actually, drones should emulate birds more than they do, and they'd be better if they did. But back to your main point, sure, there's all sorts of aspects of the biology that won't be relevant to engineering, and we don't really know what they are. And most people have said the fact that birds are covered in feathers is completely irrelevant to flying. Well, it's not for drones. I think drones would be better off with feathers. You don't know in advance which things that are important. But the hope is that you can make models that aren't that realistic about all the details, but have captured something about the essence of what's going on. Like they learn by modifying connection strengths between relatively simple processing units who communicate by just sending scalar values around the place. And that seems to be what the brain's like, and that seems to have been very successful for neural nets, for deep learning. So I think people fail to understand how much idealization goes on in science. So like the Bohr atom was nothing like a real atom, but it was a very useful model of an atom. And you could understand a lot, even though electrons don't really whiz around like the nucleus. You could still understand a lot about what was going on. And I think sort of that's where we are. And I think science is always like that. It's these simplifications that ignore irrelevant details and have enough of the actual properties so you can see the principles at work. And you never really know till afterwards which details were irrelevant. So one pet thing of mine is that we spend 8 hours a day sleeping, and so do fruit flies. And nobody knows why. I mean, it may be just so we don't stumble about in the dark, like chemicals out of the brain. That's clearly another function of it. But if you deprive people of sleep for a week, they go psychotic and they never recover. So there's something much more important going on in sleep computationally, and nobody knows what it is. And that's an aspect of human biology that most people in neural nets don't think about, but I think is something we really should think about. Sleep seems to be essential for us, and so it's got some crucial role in learning. And my current best bet is that we have contrastive unsupervised learning, where you try and take two crops of an image, or take two successive frames of a video, and you try and make their representations be more similar, and you take frames from the same video that are further apart, and you try and make their representations be less similar. And that's how you can learn interesting representations without labels. You all know this. But it turns out you can separate the phases of contrastive learning. You could have one phase in which you just tried to make things that should be similar more similar. And then you have a different phase in which you just tried to make things that shouldn't be similar not be too similar. If they're already far apart, you don't want to push them further apart. That's crazy. But if they shouldn't be similar and they're very close together, push them a bit further apart. And my current best model of sleep is that what's happening is that sleep is the negative phase. So during the day, we're just trying to make things that should be similar more similar. And at night, we're trying to make things that shouldn't be similar further apart. I have so many different theories of sleep that it's embarrassing. But I think that's an example of biological inspiration that people have been ignoring, and something very important about it. I think I've waffled long. Okay.
Hi, you mentioned you find like the neurosymbolic models where you just stick symbols on top of like a bunch of neurons and like neural nets and just relegate the neural nets to basic kind of perceptual tasks. That you find those kind of unconvincing. Like I wonder, like there's a big issue in NLP right now of like sentence representations or document representations of how you represent all the complexity or compositional meaning of a huge utterance in just like a single fixed size vector. Your
Make it a big vector.
Yeah, a big vector.
So like embeddings in models like BERT are typically sort of a few hundred components, or I don't know how big they are now, but they're not like 100,000 components, right? In the brain, they're probably like 100,000 components.
Okay, so do you think it's just like sort of a scaling thing, and there isn't any sort of explicit like hierarchies or symbolic structures that might be going on?
Oh, I think there's. Okay. The question is, are things like part-whole hierarchies real? Are parsers of sentences real? Do people really parse sentences? And I believe they do. And I believe part-whole hierarchies, both for sentences and for visual perception and for planning and for everything else, we use hierarchical structures. And if what you mean by symbolic is there's these hierarchical structures, then of course we're symbolic. But the question is, how do the hierarchical structures work? How they implement it? And so my paper on part-whole hierarchies is suggesting that it's all vectors inside. But if you think of BERT, think of BERT. So you take word fragments, and then you have many layers of representation of each word fragment. And as you go up through these layers, you get refined embeddings of these word fragments, particularly the ones that were missing. And then by the end, you can reproduce the word fragments, particularly the ones that were missing, and then you can train it all back up. But it doesn't have any kind of explicit hierarchy. It's the same word fragment all the way up. Now, the idea of my paper a year ago is that that's wrong. It works very well, but you'd be much better off doing the following. Some word fragments come in. So we're going to have hardware that's dedicated to representing those word fragments at each layer, just like BERT. But we're going to have an extra regularizer that says that I would like nearby word fragments to have exactly the same representation. So let's suppose New and York were word fragments. At the bottom level, you want New and York. Or maybe you build those out of word fragments. Then at the next level up, the idea is you want an island of identical vectors. So you want New and York to have exactly the same vector. And that vector, which is spread across two subvectors, is the representation in New York. And as you go up the system, in the middle layers of dirt, what I'd like to see is all of the vectors are identical. And what you're is whatever the meaning of the sentence notation. And that's the sentence vector. So that's a way in which you can have your hierarchy, but it's all vectors, and it's all sort of local computation with transformers to look at what other guys are up to. And all I'm doing is adding a regularizer that says, try and be exactly the same as your other nearby vectors, but only try and be the same as ones that are already similar to you. So try and form echo chambers, where you try and agree with guys who already agree with you. And what you'll get is these islands of agreement. And those will be the vector representation of a higher level entity in the part-whole hierarchy. And that's the way I propose to resolve this sort of symbolic versus neural distinction. The symbolic is just islands of agreement of these vectors. So it's all vectors, but the structure of the islands gives you the parse tree. That's the point of that paper we worked on.
Super interesting. Thank you.
Yeah, I can only say I got one terrible review of the paper, which really made me doubt it. And it was from Gary Marcus, and he said it was the best paper he'd read all year. That's the only bad thing I can say about that paper.
Thank you, everyone. Thank you, Professor, for the opportunity to talk to you in regards to the advancement in deep learning. I have a question which primarily focuses on a major problem which still today's networks face, which is out-of-domain generalization. So when one is provided with an input that is out of domain, we are still not able to generalize. And I wanted to understand, in your view, like if one is trying to solve this problem, how would transfer learning based approach can be further enhanced on top of today's current existing methods, and whether there is a need in order to take a look at what are the abstract features that are getting learnt at different layers of the deep learning network at each stage to better exploit the out-of-domain generalization, and if one is working, how to go about it?
Yeah. Okay, so one thing I believe is that if you look at people, all of the experience they've got is being combined when they have to make a generalization.
Mm-hmm.
So we've got experience at lots and lots of different things, and we see very abstract analogies between things, and we use these very abstract analogies in making generalizations, and that's why we can do generalization that isn't really out of distribution generalization, not out of the whole distribution,
mm-hmm.
but it's out of distribution with respect to some particular task, the data we've got for that one task. But we're using analogies that come from all over the place.
Mm-hmm.
So the kind of thing I mean is, if you look at, in Britain, we spend a lot of time mowing lawns, and then you have to put the grass somewhere. So you put the grass in a heap,
mm-hmm.
and it starts getting hot inside, and it can't even catch fire because it's metabolizing inside. And that's actually an explosion.
Mm-hmm.
So it's just an explosion at an extremely slow timescale, because it's something that releases energy, and that causes it to release more energy. And that's what an explosion is. It's just that normal explosions happen very fast, and a heap of grass is just a very slow explosion. So I think we make lots of analogies like that without even being conscious of it. And I think a lot of the stuff that looks like out-of-distribution generalization is we're just making analogies with things which we don't think have anything to do with this problem.
Mm-hmm.
But we're still making the analogies, and that causes us to get the right answer.
Right.
And that's an alternative way of thinking about how we can do out-of-distribution generalization. It's an alternative to the current sort of ideas about causal models, where you have to have a causal model. If you've got a causal model, it will explain everything. I don't really believe that. I think an alternative to causal model is what I think of as wild analogies. I think smart people make these wild analogies. They see relations
Right.
that other people don't see between apparently superficially very different things.
Mm-hmm.
So like the Bohr atom, it's a solar system, right?
Right.
It's at a totally different scale, but Bohr saw the analogy between, well, maybe not Bohr, Summerfield, I think, saw the analogy between a solar system and an atom. And so to really know if people, to really understand how people do out-of-distribution generalization, I think you have to say, well, for people it's in-distribution generalization. It's just they're using the distribution of things that apparently have nothing to do with this problem, but actually do at a very abstract level.
Okay. Thank you. Thank you.
Hi, Professor Hinton. I studied neuroscience before coming to AI, so you're kind of like my personal legend in research. A large part of AI, as you mentioned, has been trying to imitate how the brain works. So like from neurons to attention more recently.
Actually, I should stop you right there because when I grew up, there were two different fields. One was called AI, and that was symbolic, and the other was called neural nets, and they were opposed to one another. So I still find it very odd when people talk about neural nets as AI. And neural nets were the opposition to AI. But anyway.
I see.
But
so
no, I agree. People use AI and neural nets interchangeably, which is very confusing for old guys.
Yeah, so you've been working in this field for a very long time. I just want to get your take on kind of the future of, do you think it's possible for us to have a complete understanding of how the brain works? Because right now, like, we're kind of guessing in different aspects as you talked about. And on the other hand, like, or maybe this is like not your field, like the future of like artificial intelligence in general. Like, is it possible for the machine to get the human level of intelligence, or just like the analogies that you were talking about?
Okay, so about whether machines will get to human level intelligence. I think it would be very odd if it turned out machines got to almost human level intelligence and couldn't go any further. I think that'd be a very weird human-centric view of things. I think they're going to far surpass us. I mean, either they're not going to get as intelligent as us, or they're going to get much more intelligent. And I think they're going to get much more intelligent. I think our only hope, which isn't much of a hope, is if you ask, what examples do you have of a less intelligent thing controlling a more intelligent thing? There aren't many examples out there, but one example is a baby and a mother. So the mother just cannot bear the sound of a baby crying. It's really painful. And so the baby can control the mother, which is really important for the baby's survival. And so maybe we can build into artificial intelligences something like crying, where they just can't bear, it's wired into them, they just can't bear to see human suffering. But I'm sure I'll find a way around it. You'll get ones like Trump and Putin that don't care. And so, yeah, I think we've had it basically. That's my belief about the long term. That we're just a phase in the evolution of intelligence, and that we're going to be replaced by very smart computers. There's a long way to go because they have to be able to reproduce themselves. And but I'm also, you never get big political changes without violence. There's someone you may have heard of called Chairman Mao who says violence. I mean, quite violent demonstrations, and that's a really minor thing. So I think there's going to be lots of violence when machines replace people. But I think it's going to happen in the end, but not for a long time. I think we're more likely to do ourselves in with nuclear war, or even more likely to do ourselves in with one pissed off graduate student in a molecular biology lab could now make a virus that's very lethal, very slow, and very contagious. And that might be the end of us all. So I think machines wiping us out is not high up on the list of existential threats as other ones, but they're much more immediate and much worse. But yeah, that's what I really believe. But I think I'm not meant to tell people that.
Yeah.
Did I answer your question, or?
Yeah, I just had a quick follow-up as to like whether you think we can get a complete understanding of the human brain, like how it works.
Yeah, I think we can get a complete understanding in the same sense as a physicist has a complete understanding when a leaf drops off a tree of what happens. Now, the physicist cannot tell you where the leaf will land, right? Because that depends on a huge number of things about sort of little turbulent things in the air and all that. But nevertheless, a physicist, a good physicist who understands turbulent flow and stuff, feels they understand what's happening when a leaf drops off a tree. It kind of goes like this and falls down, and it will end up falling near the tree unless there's a big wind. They can tell you all sorts of things about it. They can't predict the fine detail of it, but they don't feel they don't understand what's happening. And I think in that sense of understand, we'll understand the brain. Yes. But I think if the brain didn't need trillions of parameters, then why has it got them? And if it does need trillions of parameters, then we'll never be able to predict in fine detail because you need to know those trillions of parameters.
Thank you.
Hi again, Professor. Before stating my question, I just wanted to bounce back on what you said earlier about sleep as something we can take inspiration from. And yeah, I thought that was like so interesting because I've also been thinking of how meditation can also like give us inspirations on how to train better models, since from my personal experience as well, like meditation has helped me reason better or make wiser decisions. But yeah, anyways, like my question is pretty related to what Yu-Chen was saying as well. And I was interested in parity with models, but I also have the vision that it's going to go beyond that. And I guess like the obvious advantage of models is the scale and the efficiency. But I was also wondering what is your vision on like how far models are going to go? Like, are they going to help us understand the world better and make scientific breakthroughs as well? And in contrast, are there any things that you think models would just not be able to achieve human parity for certain qualities that humans have?
Okay, I don't think there's anything special about people. I think we're mechanical devices, electromechanical devices, maybe in the quantum effect thing. And there's no reason why machines can't do everything we do. I mean, we're wonderful devices, but nevertheless, we're just devices. I think the future of hardware is going to be a bifurcation. So at present, all of our computers are immortal. And what I mean by immortal is that we have programs, or more recently, we have big weight matrices. And if your hardware dies, you can run the same neural net or the same program on another copy of the hardware. So the program or the weights are immortal in that sense. Now, there's a huge cost to having immortal computers, which is when you fabricate them, they have to work exactly like you think they should work. I mean, you can have some error correction and stuff, but basically, you have to fabricate them right. And you have to run them at very high power, so they're digital. So each time you run them, they do exactly the same thing. Again, with error correction, making sure that's true. And so you get huge fabrication costs, and you get huge energy costs when you run them. Now, if you're willing to give up on immortality, there's a lot of literature about giving up on immortality, and normally what you get back in return is love. But actually something far more important is very low power consumption and very cheap fabrication costs. Identical with any other individual instance of the computer. And it's going to be a neural net, of course. It's going to do everything by learning. Its weights aren't going to be the same as any other individual. So instead of fabricating it in one of these very expensive factories, you can just grow it. So this is nanotechnology. You just have a way of growing neurons and making them connect to each other, which sounds pretty biological. And what you get, if you think about a pot plant in a conical pot, if you have two different pot plants in the same conical pot, if you pull them out and look at the ball of roots, it's the same shape, it's the shape of the pot. So they're the same in that sense. But if you look at the individual roots, although they're achieving the same overall shape and occupying the space, individually they're all different from one another. And that's what these computers are going to be like. These are what I call mortal computers. You grow them. Then they get to do a particular task by learning. You can make them learn much more efficiently by using distillation. So you take an old one that knows how to do it, and you get it to give advice to the young one. And that's how the knowledge gets from the old ones to the young ones. Old ones are used to educate young ones. But when old ones get old, you just throw them away. And now you can produce these things for a few dollars each. And they can have billions of weights because they're probably pure analog. And so they run at extremely low power. Nothing has to be reliable in them. You get reliability from the fact there's huge redundancy. They're over-parameterized neural nets and they do everything by learning. And so they grow. Then the testing stage is replaced by a learning stage, which is long. And then you use them and then you throw them away. And maybe if they did well, you get them to distill their knowledge into a younger one. That's mortal computers. I think we're going to bifurcate into immortal computers, and you're going to use those for keeping your bank records and things, because you want them to be very repeatable, and you want them to be very explainable. And then you're going to have toasters that you can talk to, and you can say, I'd like my toast quite lightly done today, but the sourdough's been in the fridge for a week and it's probably quite dry, so take that into account. And you just say that to the toaster. That seems perfectly reasonable. And it adds sort of $3 to the cost of a toaster to have that interface on it. And the only way I can see us getting there is with mortal computers.
AI, or would also would there be anything left for humans to do?
I just thought it was completely unreasonable, and also it was very hard to get funding that wasn't tied to the military. So, and then those were the push reasons. There was a pull reason, which is I got off a very nice position in Canada, which had very little teaching. And Toronto is a very nice city to live in. My wife was very, very much didn't want to live in the States. So there were all sorts of reasons. But a large reason was that the money came from the Defense Department and that I didn't like politics. I never realized it would be something worse than Reagan.
I can share that sentiment, Professor Hinton. Let's have Ben next, and then we'll have Suhas, and maybe one more after that.
Hi, Professor Hinton. I was wondering if you could talk a little bit about how you go about the process of research. I assume you're involved in many projects, and how do you keep them all straight, and how do you sort of organize your thoughts around projects so that you can contribute effectively to all of them?
Okay, so I'll talk about how things used to be, because nowadays they don't keep them all straight because I can't remember anything anymore. So, but in the old days, I guess my main research strategy was to find something that everybody else agrees on that seems to me to be nonsense and go after it. So, like in the 70s and 80s, certainly in the 70s, everybody would agree that neural nets were a waste of time, that Minsky and Clapper had proved they were hopeless, which they didn't. And it just seemed to me the brain has to learn somehow, and the brain doesn't learn by people writing propositions into it. So, I mean, it's just totally implausible that we learn stuff by being told them. That's almost none of the learning we do is like that. So, it seemed to me that it was something where other people were just doing it wrong. So I think it's really good when someone says something and it doesn't sort of sound quite, it sort of feels wrong. That's what you need to go after. You need to be sensitive to that sort of niggling feeling, this isn't quite right. And go after that. Especially if everybody is agreed on this silly thing. So I think that's how you do original research. You go after the ways in which the current opinion is wrong. And that's why graduate students are kind of the best originator of new ideas, because they haven't been indoctrinated. They know enough to sort of be able to understand the problems, but they haven't yet been fully indoctrinated into the current way of thinking. So I was very fortunate in that my advisor, unlike almost all advisors, said that don't read the literature. First, read enough of the literature to know what the problems are. Then think about how you'd solve the problem. And once you've figured out how to solve the problem, then go and read the literature to see if it's been done already. And that's kind of my strategy. There are people like Schmidt who think this isn't the right strategy, but there you go.
You were talking about like the threat of adversaries, and what I've seen in like the research for like adversarial robustness is that there's a lot of different techniques. Many of them seem to be patching up like the current like neural network structure. A lot of them come up with like new model architectures that happen to be more robust. But in terms of like solving this sort of problem, do you think that, or not just this problem, but all the problems in general, do you think that we just need to do really sophisticated patch-ups of like current neural networks or the current like architectures, or do you think at some point we're going to evolve past like neural networks to solve our problems and we're going to go into a completely different type of solution for these things that we can't even like fathom right now?
So I don't think it's just a question of patching up the current architectures. I think it's a question of having architectures that are somewhat different. Like I was talking about with BERT, you can have a version of BERT where you try and make neighboring fragments of the next level up have the same representation. And gradually as you go up, you get bigger and bigger islands of identical vectors. And those are the larger things. So if you give this system a sentence, in the middle there, all the vectors will be identical, and they'll be the vector representation of the meaning of the sentence. And they'll just be saying, at every location here, at the sentence level, this is what's being said. And then sort of halfway up, at every location at the phrase level, this is what's being said here, and this is what's being said there. If you think of that as just a patch-up of the architecture, then yeah, maybe you can patch it up. But I think of that as a fairly radical departure from the way things work now. And I think once we get to architectures like that explicitly parse things, then a lot of these adversarial issues will go away. I don't see how an architecture like that could look at an ostrich and say it's a school bus. I mean, you just can't do it as far as I can see.
Thank you.
So we probably have time for one more. So we'll go to Alex.
Okay, yeah. So, yeah, it sounds like you're not excited about things like symbolic approaches or causal approaches. You're excited about things like particle hierarchies. Are there any other ideas that you think are particularly promising?
No, that's your job. I'm giving a lecture today. I'll talk about some things about different timescales. So I think we've hardly explored at all using multiple timescales for weights in a neural net. And the reason we haven't explored it is because memory fetches are expensive. And once you fetch some weights from memory, you want to reuse the same matrix of weights many times on many different training cases. And that means you can't make the weights be a function of the history of that training case. And so you can't have weights that are different for every training case. It just costs too much with current architectures. And so there's a hardware reason why people aren't exploring what seems to me what biology is telling you, which is synapses adapt at many different timescales. We're not doing that. And you get a lot of interesting extra properties out of that. So that's what my talk will be about. There'll be some pieces of work I've done in the past that relate to that issue.
So I am the keeper of the time in this case, and cognizant of the fact that Professor Hinton actually has another meeting after this one and might want just a moment for a breather, for air between them in this case. So please join me in thanking Professor Hinton for joining us in all of our conversations and all of your great questions. I realize we didn't get to all of you. I'm sorry. I know the hour goes by a little quickly in this regard. So please join us at the lecture, and then hopefully we can ask it as a part of that moderated Q&A in that case. So thank you all.
Thank you.
Thank you.
Take care, everyone.
Bye.